And remember, for the polymers, what we wound up with is that the energy was proportional to the curvature squared, and we actually derived that. Here, we are going to have a similar thing. The energy cannot be linear in the curvature for various reasons, and one of them is that if we would have an energy that's linear in the curvature, then this shape would, we say, with a positive curvature, and this shape with a negative curvature would have the opposite energies, and that obviously cannot be the case. So however, what we can have is what's known as a spontaneous curvature. Right? This piece of paper is naturally flat, but a lipid bilayer could have, say, lipids with larger heads on the outside and smaller heads on the inside, that the rest state is already curved. Right? A familiar object that has such a curved rest state is a banana. Now, to write then down what the full energy is going to be, what we will have is a term for the curvature which is going to be quadratic in these principal curvatures. And so if I write down the most general form of that, what we have, the energy of the curvature is going to be an integral over the whole surface, since we need it just like for the polymer, where we had to integrate over the whole length of the polymer. Here we're integrating over the whole surface. And what are we integrating? Well, so there are going to be a couple of factors too, which are simply for historical reasons and being consistent. So we are going to have a spring constant, essentially, which we now going to call the bending modulus. Unfortunately, this one is also called kappa, so not to be confused with the eigenvalues kappa 1 and kappa 2, over 2 times 2 times the mean curvature minus any spontaneous curvature, which is typically written as C naught, squared. Because of this argument that I just gave, we have deviations in the positive or negative direction should count in the same way. Plus a second term, which is typically written as a K with a bar, or something with a K with a sub G, times the Gaussian curvature. That one is already quadratic. It's already K1 times K2, so we're going to leave it like this. And this one we are going to integrate over the whole area. So this is the curvature energy contribution to the energy of membranes. Usually we combine this with another property, which I already alluded to, the same as for soap films, which simply in some sense has to do with the fact that the membrane, so this curvature comes from the solid property, the elastic bending energy. The membrane, like the sheet of paper, is effectively incompressible. If you want to stretch the membrane, it is very hard. However, the membrane, unlike this piece of paper, is living in an environment where it can fluctuate a bit. And typically what will happen is that the membrane will not be in a completely stretched shape. It will have some wrinkles. And that wrinkly shape is going to allow us to change the area a little bit. The amount of energy that we will need to input to pull out the wrinkles or to compress and then create more wrinkles is entropic in origin, but it will simply scale with the amount of area. And the proportionality constant we call the surface tension, which is just the 2D version of the pressure. And so we're going to have a second term in our energy, just like we have the PDV term in the regular energy as for work, for compressing or extending a volume of gas. We will have a surface tension times area term for compressing or stretching our membrane. In some sense, you could also, let me first write it down. Right? So we are going to have a tension, which is surface tension, which I'm going to write as sigma times the total area, or I can write this as an integral over the total area. In some sense, you could also interpret this as a fluid contribution, or more specifically a liquid contribution, where you say that this fixes the area. If we would say, well, we have a total area that cannot change because the membrane is incompressible, then what do we want to do? Well, we want to include this as a constraint in our system. We don't want variations of the area. So what do? We add a Lagrange multiplier to our energy, and then taking the derivative to the Lagrange multiplier itself, we say that the total area is fixed. In that case, we don't, of course, want the total area, because then we would say that this is 0. We would write this thing as A minus some reference area, like that. But of course, sigma times A0 is just going to be a constant number, so nobody actually writes that thing. The right interpretation of this term is something that will still get physicists heated up. The term can even be interpreted in two ways, because you can say, well, in some cases, right, you can add these wrinkles and pull them out. You could also maybe add lipids and pull them out, and remove them from the membrane, and that would be more a term like a chemical potential times dN. And so if we take that and we say, well, every lipid has its own fixed area, then this can also be interpreted as a chemical potential times a number of lipids in our system. In the end, the ensemble in which you work determines how you interpret this. If you work in a fixed area or a fixed number of lipids with a fixed area per lipid system, then the interpretation of this thing is that it is a Lagrange multiplier that fixes indeed this constraint. If you work in a fixed surface tension ensemble, you say, well, the area can change because the total area, the projected area can change, not the total area, but the projected area, because if I put in a wrinkle, then the distance between my hands becomes less, even though I'm not removing any real material. Then you allow the area to fluctuate, but the surface tension remains fixed. Both of them are valid ways, and in different applications, and especially in different experiments, you will effectively fix one or the other, and therefore both of them are valid ways of looking at this energy. Now, the total energy, of course, will be the sum of these two. Depending on who you ask, only the curvature energy or the total energy has a given name. It is usually referred to either as the Canham-Helfrich or just the Helfrich energy, after the people that first started applying this thing to membranes in the early 1970s. People have looked at this energy functional before, but really applying it to membrane theory was done around that time. So let me explicitly write it down. So we have the Canham-Helfrich, I'm going to call it like that, Canham-Helfrich energy. It's simply the sum of the other two, and of course the surface tension I can pull inside the integral because it's a constant. And so we will have the integral over kappa over 2 to h minus c naught. As I already said, if we have a closed surface, and this is the Gauss-Bonnet theorem, the integral over the Gaussian curvature will give me a constant. Right? So then we have that the integral over the closed area, so I'm going to write this with this little loop so that we indicate a closed surface of k times dA. It's going to be a number that depends only on the genus of the surface, which means the number of holes. And in fact, you can calculate this, and this is 4 pi times 1 minus the genus, which I'm also going to write as a g. So for a sphere, g is 0, and so this number is going to be 4 pi, and you can easily check this for yourself. For a torus, we have 1 hole, and the number is actually 0. And for say a double torus, which has 2 holes in it, this is going to be a negative number. And this difference is going to be important. In biology, this mostly shows up when you are trying to punch a hole into a membrane, for instance, because you want a cell to split in two. And there is an energy barrier for that, and that comes because of this Gaussian curvature term. For simple shapes, if we just want to calculate what the shape changes is under small effects, this number is simply going to be a constant and we can ignore it. For a spherical membrane, we can also easily calculate what the mean curvature contribution is going to be. For a sphere, the mean curvature will turn out to be independent of the radius. So how do we do that? Well, remember the mean curvature was the average of the two principal curvatures. And for a sphere, it doesn't matter in which direction I look, the curvature will always be the same. Right? So specifically for a sphere, we have that kappa 1 and kappa 2 are the same, and they are simply 1 over the radius of the sphere. And so the mean curvature will be, well, a half of kappa 1 plus kappa 2. That's just 1 over r. And the Gaussian curvature will be 1 over r squared. And you can see immediately now the previous statement, right? Because the area of a sphere is 4 pi times r squared. So if I calculate, if I integrate the Gaussian curvature over the area for a sphere, I need to get 4 pi. For the mean curvature contribution, well, if you have a sphere with 0 spontaneous curvature, then the integral of 2h squared over the area, well, for a sphere, the curvature is constant, so I can pull that out. So I have 4 pi r squared for the area, and then I have 2 times h, and so I have times 4 divided by also r squared. So I have 16 pi, but independent of r. Typically, we include the kappa over 2 here. So we have kappa over 2, and we have the curvature energy of a sphere equals 8 pi times kappa. This result is mathematically very simple, but it carries in itself something fundamental, and that has to do with the stability of membranes. If I now look back to the Canham-Helfrich energy, I see I have 3 contributions. I have the mean curvature, I have the Gaussian curvature, and I have the surface tension. So if I also calculate what the surface tension contribution for a sphere is, then what we have is, well, this is sigma integral dA. That's going to be 4 pi r squared sigma. And so if these were the only contributions, well, the Gaussian curvature contribution is independent of the radius, the mean curvature contribution is independent of the radius, the surface tension will be proportional to the radius squared. So that would suggest that the surface tension will always shrink our sphere to 0. Now, of course, that doesn't happen, and the reason for that is that our sphere or our membrane will typically have a fixed and closed volume. Over time, a membrane can change its volume because water, even though it doesn't like to go through the membrane, can go through the membrane, but it goes very slowly. You can stimulate this by putting a difference in pressure inside and outside. And indeed, this is what the surface tension will do. So really what we should do to describe the energy of a closed surface is we should add a term for the volume to the Canham-Helfrich energy. And there, really, the volume is fixed. So the number in front of the volume will be a Lagrange multiplier that we set. And that, of course, will simply be the pressure. Right? So we add one more term, minus P times V. And the minus, of course, is because of the standard definition of the pressure, the difference there. And then what we say, well, if we have the sphere, the volume of the sphere, we know this is 4/3 pi r cubed. And now, because the pressure term comes in negative, the combination of these two will give us an energy which is 4 pi r squared sigma minus P times r over 3. And this energy can change if we change the radius of the sphere. And to find the equilibrium radius, of course, what we do is what we always do. We take the derivative to r, the curvature terms will drop out. And from the other two terms, if we take the derivative of r and put it equal to 0, what we find is that we have 4 pi times r, 2 times sigma minus P times r. And therefore, the equilibrium radius equals 2 sigma over P. This relation is known as the Laplace law. It also applies to simple say, water droplets in air, spherical ones. And also there, the surface tension and the pressure difference between the inside and outside are related and set the equilibrium radius of the droplet. Now, another thing that we need to take into account, though, is that I said the Gaussian curvature will be independent of the size of the sphere, and in fact it will be independent of the shape of the closed surface as long as we don't punch any holes into it. But perhaps we could have a spontaneous change of one sphere into two smaller spheres. So how could that happen? Well, that could happen if the Gaussian curvature term would give us a negative contribution. Right? Nobody told us that the bending modulus and the Gaussian modulus are positive. Well, the bending modulus better be positive, because otherwise everything will run off to minus infinity and nothing will happen. But the Gaussian modulus, in fact, will turn out to have to be negative. So if we look at a sphere and we simply look at the bending contributions, right, what we find is that for one sphere, we have 8 pi kappa plus 4 pi kappa bar. And for two spheres, what we get is double this. So when is this going to be dominant? Right? So we have 16 pi kappa plus 8 pi kappa bar. And so if two spheres are favored over one sphere, that means that this number has to be less than the number of one sphere, 8 pi kappa plus 4 pi kappa bar. So this is the unstable condition if the energy of the two spheres is less than that of the one sphere. So for a stable sphere, of course, what we need is the other way around, and therefore a sphere will only be stable if kappa bar is larger than minus 2 kappa. So kappa bar in practice will turn out to be usually a negative number, but it has to be larger than minus these 2 times the bending modulus. Other than that, we can typically forget about it, again, because of this Gauss-Bonnet theorem that tells us that we can simply integrate it out. All right, so we have seen what we can do with a sphere, and the steps I have tacitly taken are steps that we are going to use in more examples. Right, so what we can do is we can calculate what this Canham-Helfrich energy is for a certain situation. And then we can look for equilibria simply by doing what we always do, and we say we look for minima of the energy. Now, one way to test a model like this, which is what physicists like to do, is by taking the system and perturbing it quite significantly. Now, how you perturb this depends on what kind of physicist you are. If you are a high-energy physicist, typically you perturb things by smashing them together. However, if you are a biophysicist, you know that smashing cells together will usually just result in a big mess. And rather than building particle detectors for big messes, what you say is, well, can't we be a little bit more subtle, and rather than smashing things together, pull things apart? And indeed, this is what you can do. What you can do is you can make a membrane vesicle in the lab. This is pretty straightforward. And now, because we have certain tools known as optical tweezers, what we can do is we can bring a bead, a glass bead, that we trap in an optical tweezer. We coat it with some proteins that stick to a membrane, and then we pull with some force on this bead. And then we see what happens with the membrane. Well, so two things might happen. You might drag the whole membrane. This is not what we want, so we typically fix it on the other side. Typically, people put in a pipette on this side and maybe suck up a little bit of the membrane to control the tension, and then pull with a force. And what happens is that initially the membrane will deform a tiny little bit, but after an initial deformation, you will see a remarkable, what we call a shape transition. And the membrane will start assuming a cylindrical shape. So what it will do is it will have a shape that looks like this, where there's a little hole here, and I'm exaggerating the size of this hole, and then it will have a tubular deformation. And here is our glass bead. This is a shape that is actually observed quite a lot in cells, where of course there's not optical tweezers that are pulling on things, but molecular motors, but they can actually make these tubular membrane shapes. And in fact, in the ER, which is one of the organelles inside your eukaryotic cells, most of the membrane exists in tubular forms. Now, why is the tube such a common form? Of course, because the tube will turn out to be a solution to this Canham-Helfrich free energy solution, meaning a shape that minimizes it, under the action of an external force. Right, so if I have applied this force, I have of course done some work, which is the force, and I'm going to call it a little f to distinguish from free energy, times the displacement. And so if I want to calculate the equilibrium shape, we do the same trick as that we have many times before. We say, well, we apply the principle of virtual work. The energy is the energy minus the work applied. In this case, because a tube is open at both ends, material can flow in and out, so the volume is not conserved, so I don't have to add this volume term, but we do have a penalty for changing the area, so I'm going to include the area term. Right, so what do we have? Well, if we zoom in here and we write this really as a cylinder, what we can say, well, the cylinder, what are the mean and Gaussian curvatures of that? Well, the cylinder, it is curved in only one direction, so it has a non-zero curvature, which is 1 over the radius in the curved direction, but it has a 0 curvature in the other direction. So for a cylinder, I'm going to have a mean curvature of 1 over 2r. I'm going to have a Gaussian curvature of 0, and indeed the cylinder has a hole. And if I would close the cylinder on itself, I would get a torus, so that's consistent with the observation or the Gauss-Bonnet theorem statement. And the area element, and since this is again a constant, right, the area of a cylinder is of course 2 pi r times the length. So if I plug all this in, the energy of this cylinder will be, we have kappa over 2 times 2 times h squared, so the 2 kills the 2.5, so we have 1 over r squared plus the surface tension times 2 pi r times L minus this extra energy due to the work that we have done. And now if I want to find the equilibrium, of course what I should do is take the derivative with respect to the relevant variables, but now there are two. We have an r and an L variable, and then so we should say, well, both of them should be 0. So we have that 0 is the derivative of E with respect to L. That's an easy one. That gives us that this whole thing minus F equals 0. So this gives us a way of calculating what this force should be if we know the radius. And of course the radius we're going to get from the other one. And this one is a bit more work, because the first term will have a 1 over r, so this becomes a minus 1 over r squared, so we have 2 pi L, and then we have kappa over 2 times 1 over r, derivative of 1 is that, is minus 1 over r squared, plus, and then the sigma term, of course, just had an r, so this just remains sigma, and the F times L is independent of r. And so this one gives us a number that's independent of the length. And so we're going to get that sigma equals kappa over 2r squared, or the equilibrium radius is given by kappa over 2 sigma square root. And now if I plug in the equilibrium radius into this other equation, I can also calculate the equilibrium force. And that will turn out to be 2 pi 2 times kappa times sigma. Now if you look up the material properties of a typical membrane that people use for such experiments in the lab, what you will find is that kappa is on the order of 10 to 20 kBTs, sigma is of the order of a few piconewtons per nanometers, or a few tens of piconewtons per nanometer. And if you plug these two numbers in, what you will find is a typical equilibrium radius between, say, 30 and maybe 50 or 80 nanometers, so much smaller than the lateral size of a membrane, but still significantly larger than its thickness, and the typical force on the order of maybe 25 piconewtons. And indeed, you can measure this, and this turns out to be exactly the case. One thing that is remarkable is that the force will be independent of the length of the tube. So this tube does not behave like a classical spring, where the force would be proportional to the length. It's independent of the length. So if I pull a longer tube, I will retain the same force, and indeed, this is what you see in the experiments. Measuring the radius in experiments is very hard because this is below the typical optical resolution, but if you control the surface tension by squeezing this pipette here on the left, you can see how the force gets affected, and because the radius shows up in the force, we can infer that this is indeed the case. In fact, if we now plot the force as a function of the extension, and so we have a force extension curve just like we had for our polymers. Initially, we will not yet have a tubular shape, so we will simply deform the spherical shape just a bit, and then the force is proportional to the extension, so we have a version of Hooke's law. But then we have this shape transition, which typically corresponds to some force overshoot, but then we have this equilibrium value. As you may know, a typical kinesin motor in a cell can exert a force of about 5 piconewtons, so a single motor cannot do this, but a couple of motors working together can do this, and this too is something that can be done in experiments, and also has been done, among others, by people that are working in the bionanoscience department. Measurements of this thing show that indeed you have this overshoot. Typically with an optical tweezer setup, the overshoot is much larger than what I've drawn here. But this is something that can be tuned by pulling more slowly. And there is also research going on right now where people are measuring these kind of forces and using them to construct more complex structures inside the BN department, but also in other labs around the world. So recapping, what have we seen and what have we done? Well, we have constructed a model for describing membranes, which is a generalization of the model of polymers, where what we started with is a way of describing the membrane shape in 3D with this local coordinate system that is based on the tangent vectors, which are simply the derivatives of the embedding function, this vector r. We then looked at the curvature of this membrane, and we found that we can write this either as the divergence of the normal, and I haven't proven that this is the same thing, but this is again something that you can look up, or as the average of the eigenvalues of the curvature tensor, which is given in terms of the second derivative of the embedding or the first derivative of the tangent vectors, which is the same way as that we did it for polymers. This gives us two invariants because we have a two-dimensional surface now rather than a one-dimensional object for the polymer, which are known as the mean and the Gaussian curvature. And then I invoked the Gauss-Bonnet theorem. It's a bit more work to prove that, but that too can be done. That says that the integral over the Gaussian curvature over a closed surface is always a constant. So for the energy, as long as we're not punching holes in the surface, it's not going to matter. But the mean curvature will change. Then we also have a contribution from entropy or from the liquid nature of the membrane, depending on your point of view. That gives us a surface tension term, which is essentially the same as the pressure times volume term that we have in standard thermodynamics. And if we have a closed surface, we also need to take into account that the enclosed volume is in many examples conserved. So all that combined gives us an energy functional. And this energy functional then we looked at for two simple examples, the sphere and the cylinder. And in next week, we are going to look in more details. We are going to look at fluctuations of this thing and also at different shapes of the membrane that we might encounter.